I'm going to talk about section 2.3. In this lesson, 2.3 is about functions. So if you'll notice, there's a real important definition in your book on section 2.3 that tells you what a relation and a function is. So I'll take time to actually write this down. We don't always do that, but here it's just a really important foundational definition that we use. So first of all, a relation is a set of ordered pairs. So that's very loose. It's just anything where you've got an x and a y in ordered pairs, or even two real things that you're comparing, an x and a y. That makes a relation. And so we graph relations with ordered pairs. But a function, so the title of today's lesson is a special relation, so xy pairs, a special relation in which for every distinct value of the first component, which normally is x. We normally do an x for the first component, y for the second. We call that our ordered pairs. But actually it could be other letters. If we were doing like an application, we could be comparing real life things. But in our generic math algebra world, we use x's and y's. So the first component, normally x, there exists exactly one value of the second component, which we usually use the y variable. So in a function, for every x value, the first component, there can only exist exactly one y that corresponds to it. What that's really saying in kind of more easy to understand terms is there's no x value that's repeated. If you see a list of ordered pairs, for example, one way to think about this to decide if something's a function, and this would be like your example in your book, say like on example 1, it says determine whether these are functions. Now, we don't normally do it just exactly like this, but kind of to get this discussion started, let's say we had a list of ordered pairs. The ordered pair 1, 2, the ordered pair negative 2 and 4, and the ordered pair 3 and 4. And it'd say, would that be a function? So just going strictly by this definition, is that x value ever repeated? It is not, so we would say yes, it's a function, yes. The next set of ordered pairs, set G, we have on ordered pair 1, 1, 1 with 2. Oh, you can see it's not going to be okay there. 1's with a whole bunch of things. So that x value is definitely being repeated. So there's a first component with the number 1, that same x with the number 2, and even a third example with the number 3. So if the x value gets repeated with different values for the y, that goes against what we just wrote down, talked about here. So we'll say no, not a function, not a function. All right, one more example here. We've got set H and a list of ordered pairs, negative 4 with 1, negative 2 with 1, and negative 2 with 0. All right, so oh, did I write that right? Oh, not a function again. I was going to say it's okay if the y value repeats. This was not a problem. The y value repeating is actually okay. But I do see the x value is repeating. I've got negative 2 with 1 and negative 2 with 0. So nope, not a function again. So that one is a big no as well. So really, if you just see ordered pairs, just look to see if the x value is repeated. If the x is repeated, just say no, not a function. All right, so that's one way of telling if a relation is a function. The second way is by graphing. So on example 3, we'll come back to example 2 in a minute. On example 3, we've got some graphs. One is a graph with just some points around. You've got a point over here at negative 1, 1, a point at 0, negative 1, and a point at 1, 2, and a point over here at 4, negative 3. So none of those x values, when you look at that graph, none of the x values are the same. And also you can tell it by here, this is an x, that's where that one crosses the x. None of those overlap. There's no x value repeated. So we would say those 4 points would represent a function. On graph B, the second example, we have this ellipse, oval looking shape. And we can say this would not be a function because if we were to think about, say, this x value at 1, there's an x value at 1 that has a point up here on this curve. Say that's at 3, I don't know exactly. but also this point at 1 is at a value down here, say -3. So you've got an x value here corresponding up here on this graph and down here on the graph. So repeating, this x value goes with two different y values. That would also go against the definition. And there's many other examples, like back here, say at -3, it hits it up here and down there. So about any place you look at it, there is one x value, you know, along our x-axis, any x value we pick is corresponding in two places. Now, a quicker way to think about this, and what the book would recommend here in just a minute, it shows, is something called the vertical line test. So the vertical line test says, and that's a C, vertical line test says if you can draw a straight up and down vertical line on your graph and it hits the picture, you know, the curve, whatever you've drawn there, the graph of it, if it hits it in more than one place, it can't be a function. And it's because what I said, that's an x corresponding to two different y values, or an x that's repeated with different y values, going against the definition. So that's the vertical line test. If you hit it more than once, not a function. So this thing is definitely not a function, no on that. All right, the next one, the next example C, we have a line, a linear equation. Now those are what I call the friendly line. Friendly line because it's the easiest of our graphs to deal with. It's just one slope there. There's no tricks and turns or twists in it, just straight on line. So there are always functions. If you draw a vertical line, any place you can draw a vertical line, you can only hit that line in one place. So lines are always functions, any linear equation. I guess the exception to that would be as if it was actually a vertical line itself. The vertical line, like x equals a constant, is a vertical line, so it's not a function. But any other line, our typical lines, are always okay. Okay, then example D, we have our U shape, our parabola looking shape. We're going to be dealing with parabolas a little more later in the chapter. But a parabola, if we draw a vertical line, you can only hit it one place. So the vertical line test holds on it to make it, yes, a function. All vertical lines just touching along that actual picture of the graph once. So that one is yes. So the lines and our upward, downward parabola U-shape, those are always functions, yes. All right, the next thing that we discuss in this section is domain and range. That's kind of the big three things in this section, is this idea of what is a function, and then domain and range. So next, let's write down about domain, a note about domain. Domain is how wide the graph goes, is one way to think about it. What you can plug in for x and get a real answer for y. It has to do with the x values of your graph. Again, it's what you can put in for the x value and get a real answer for y. What you can plug in for x, if you were doing, say, a t-table, you'd plug in values for x, plug in for x, and get a real answer for y. All right, we'll look at some examples of that in a minute. And then the range is, what are those y values? So normally we think of the range or the y values as being the dependent values because they depend on what you plug in for x. You kind of get the output for y. So they're called dependent values. But the range is what you get, what y values you get. You get from this process of plugging in, say you're doing an equation, you're looking for the domain and range of an equation. What are the output values? You know, if you were making a t-table to graph any type of equation, so the domain is what you can plug in for x and get a real answer over here for y, and the range is, well, what are those answers? What kind of answers do you get for y? All right, so let's look at an example of that. So a lot of equations, we can just plug in anything goes, like with our line. Let's say x plus y equals 7. That's a linear equation. And if I were making a t-table to graph it, that's one way to graph a line, is just by plotting points. I could plug in anything my heart desires. I can plug in 1. 1 plus what is 7? There's a real answer for that. And you can solve and get that. Y is 6. So 1 is in the domain. I can plug in 2. 2 plus what is 7? And we'd solve and get 5. So you could plug in 2.5 if you felt like working with fractions. You could plug in a fraction. 2.5 and 4.5 makes 7. You could plug in a decimal, 2.1 and, let's see, 4.9. You can plug in decimals, you can plug in fractions. Can I plug in a negative number? Like -1 plus what makes 7? Let's see, we could solve that equation and get 8. So you could plug in any number that your heart desires, and you're going to get an output, a unique output even for y. So there's no overlapping here. No x is ever repeated. Again, we said lines are like that. They're always our safest ones that we graph. They're yes to everything. So if we were to plot these points, to graph a line, you really don't have to plot all those points. We know that it just is straight as a stick. So, but you can plot a few to see, like 1 and 6, over 1 and up 6 is here. Get this out of my way here. We could do this all day long, by the way. We can plug and chug, find values that solve this equation. These are just some sample ones. Usually we plug in 0. 0 and 7, that's a good one to plug in. Okay, so 0 and 7, let me just use that one. -1 was up 8, over 2 is up 5. I've not drawn my graph just really great, but you can see I could then connect some of those dots, and I know it's going to make a line. So another way to think about domain would be thinking about how wide does it get. Visually, if you have the graph, on the T-table, you can see I could do this all day long, and for the rest of eternity, I could think of things that add to make 7. There's infinite values that work there. So we would say the domain, what can you plug in for x? Anything. Any number from -infinity to +infinity goes. Any number your heart desires, you plug it in, you're going to get an output for y. And then what kind of answers did you get for y? Well, it looks like they're all over the place here too. I don't have enough sample to really prove this to you, but you're never going to get a repeated value on this either. Anything. You could get any type of number for y. So the range is also infinity to infinity. But probably an easier way to think about this domain and range thing is if you have a graph, if you're looking at the picture, domain is left to right. How far does the graph go from left to right? Looking at it this direction, that's the x-axis. This graph goes on to infinity to the left, and it's going downward, but it's going to the right as well. It's going left and right, never stopping. So that also tells us the domain, the x values keep going left and right, infinity, infinity. Also for the range, the same argument. It's a little more up and down. Maybe you see that a little more visually, but it's also going down to -infinity, thinking about the range, the y value. It's going down, it's going up, and it just keeps going. So there's no restrictions on that. So and that's how it's going to be. Again, I call that your friendly line, like the L-I-O-N, the friendly line. Maybe I know that from my kids watching cartoons back in the day. But this one's the friendly L-I-N-E, the friendly line, because it's always a function, and their domain and range, there's no restrictions. Just anything you want to plug in works, no restrictions on anything if it's a linear equation. And again, what makes a linear equation is when x and y are both to the first power. So let's say you had y equals 3x plus 1. This is rearranged a little differently, but I still recognize it's a line because x is to the first, y is to the first. So I could make some points on that, like C0, 1, and 2, or some easier numbers. When I plug in 0, 3 times 0 plus 1, and work that out and get y equals 1. I can plug in 1, I'll get y equals 4. Let's see, 2 is 7. I can do that all day long too. Whenever I plot those points, I'm going to get, again, a linear equation. I'm running out of time, so I won't get to do that with you. We'll have to continue. But notice that it's opening left and right without bound and up and down without bound. So once again, there's that infinity. And I don't even have to graph it to know it. If I know this is a linear equation, I know that's the domain and the range.